Hello everyone and welcome to the 8th recitation of Intro to Deep Learning. We will be covering CTC decoding and beam search in this recitation. The recitation will help you with both parts of homework 3, so please make sure to review the slides and code and feel free to post any questions on Piazza. So let's get started. In the lectures, we have seen how to train sequence-to-sequence models where the output is order synchronous but not time synchronous. We started out by using the Viterbi decoding algorithm and then discussed training using the forward-backward algorithm. We will now discuss how to obtain the output sequence from the predicted probability distributions during inference, where we don't have the correct order of symbols provided like we do during training. However, before we talk about the beam search algorithm that we use for decoding, there is a key decoding problem that we need to address. Suppose we have the output symbol sequence shown on the slide, such as R, 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 O, 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 D. On merging the duplicate symbols for the final symbol sequence, are we supposed to interpret it as ROD or ROOD? Basically, how do we distinguish between repetitions of a symbol in the final sequence and an extended symbol sequence that represents the same instance of a symbol, which is meant to be collapsed to a single symbol? Basically, how do we encode repetitions in a symbol sequence? So, a solution for this would be to introduce a new symbol, a blank, which serves to separate different versions of a symbol. Thus, all the discrete versions of the same symbol must be separated by a blank, otherwise they are collapsed into a single symbol while doing the final decode. So, you can consider the examples on the slide. When you see an example such as RRR followed by blanks, followed by OO, followed by blanks, and then DDD, you see that the instances of the same symbol, which are not separated by a blank, get collapsed to a single symbol, and similarly those which are separated by a blank are recorded as two separate symbols. However, when the symbols do not belong to the same character, you do not require a blank separating them, because it's pretty clear that you are not supposed to collapse them into the same symbol. So using this, we can solve our problem of encoding repetitions in character symbol sequences. And now this symbol set with a blank should be recognized by the network, and the network should be trained with this extra blank to be able to predict the probability of this extra blank as well. So this is how the probability produced from the forward pass will look. An extra row is basically added for the blank symbol along with the rest of the symbols in the symbol set. And while decoding for training, you modify your graph as shown. Basically, you add a row of probabilities of a blank being produced at that particular time step between every two characters, and also at the start and the beginning of at the start and the end of the symbol sequence. This is because in the output symbol sequence, you could predict a sequence of blanks between any two characters or at the very beginning and end, and these rows are to provide for such scenarios. And then you train just as before using the Viterbi algorithm or the forward-backward algorithm. So the overall framework that we just saw is referred to as CTC, or Connectionist Temporal Classification. Basically, this framework is considered whenever the output sequence length is less than the input sequence length, or basically when duplicating labels at the output is considered acceptable. So you can produce a series of O's to represent a single symbol O, or you could also produce blanks at multiple time instances, since the output sequence length is lesser than the input sequence length. So, now that we have addressed the challenge of being able to decode multiple instances of the same symbol without ambiguity, we return to the decoding problem in this CDC setting. We could use a greedy approach for this and just choose the symbol with the highest probability at each time step and then merge this symbol sequence. However, this will obviously be suboptimal. Basically, at test time, you will be performing a simple argmax over the entire column of probabilities over all the symbols, and thus finding the most likely time synchronous symbol sequence instead of the most likely order synchronous symbol sequence. Another possible way would be by simply enumerating all possible decodings of the probability matrix that we have, using the probability matrix that we have, and basically obtaining all possible symbol sequences that could be decoded. And then we calculate the forward probability of each of these sequences and pick the one with the greatest probability. While this solution will definitely be correct, it would require the explicit computation of an exponential number of sequences, and because it is so inefficient in terms of time and memory, one possible solution would be to try and organize all of these symbol sequences as a semi-tree first. So, if you consider the hypothesis semi-tree shown in the figure to the right, um, first of all, you must notice that the vocabulary has only three symbols here, namely S1, S2, and a blank. In fact, from this slide onwards, you can assume that the vocabulary will consist of only three symbols. Next, every symbol connects to every other symbol other than itself, and a symbol such as S1 could also connect to itself through a blank. And this symbol structure that you see between S1 to a blank and then to S1 or S2 is repeated recursively at every node. And finally, every node represents a unique symbol sequence, such as this particular node represents the sequence blank S1, and this particular node represents the sequence blank S2, blank S1, and so on. Now we consider this following trellis-like structure for decoding the graph from the tree. You see that in this trellis, it is the symbols to your left are basically the same symbols in the semi-tree, but they have been unrolled over time. So the green nodes represent the upper half of the semi-tree and the pink nodes represent the lower half of the tree. At each node, we obtain the alpha or the forward score of a unique symbol sequence. We then use this trellis to select the symbol sequence with the largest alpha or forward probability. And now, in practice, while listing out all possible symbol sequences can be the right solution, it is also exponentially large in terms of time and memory. So we employ a strategy called pruning, and this keeps our graph computationally manageable. And yeah, so this is basically the core idea behind beam search. In beam search, you maintain a beam of a fixed width k at each time step and prune out symbol sequences that show lesser promise, retaining only the symbol sequences with the k highest probabilities, or the best case symbol sequences at each time step. Now we look at the beam search algorithm and go through it step by step. Certain global variables that you must know of are path score, which maintains the scores of paths ending with a symbol; blank path score, which maintains the scores of paths ending with a blank; symbol set, which contains all the symbols excluding the blank; and finally y, the matrix of output probabilities with dimensions n into t, where n is the number of symbols in your vocabulary and t is the number of time steps. So let's start looking through the algorithm. We look at its first step, which is to initialize the paths. So the initialize paths function takes as its input the symbol set and the output probability matrix at time step 0. At time step 1, so the first output probability vector, and as its output you get paths which either terminate with a blank, a symbol, and also the dictionaries of their corresponding forward probability score. So this figure illustrates the step that we are looking at. We basically aim to initialize all the paths which are either S1, S2 or blank, and also initialize their forward probability scores, which would basically be the probability of that particular symbol occurring at the first time step. This function represents the initialized paths pseudocode here. Notice the variables initial blank paths code and initial paths code. These are dictionaries of paths which either end with a blank or end with a symbol, or in this case are a blank or are symbols. And then the initial paths with final symbols and initial paths with final blank are sets which have the path themselves, which would be either a blank or a symbol. And you simply initiate the initial paths with final blank with a blank or null symbol, and then you initialize the score of that particular path with the probability of a blank occurring at the first time step. For the symbols, you would do something very similar, but you would first loop through all the symbols, initialize the path with that particular symbol, and then initialize its score with the probability of the symbol at the first time step, and add the path to the set initial paths with final symbol using set addition. And finally, you return all these sets of paths along with their corresponding dictionaries of scores to the main function. In these dictionaries, basically the key is the path and its value is the forward probability of the path occurring. So now we start with the loop which spans over all t time steps. The first step in the loop would be to prune the collection of existing paths. However, we will be discussing this at the very end to avoid confusion. So let's skip forward to the next function, which is to extend with blank. So this function basically tries to extend your existing paths with a terminal blank. So as its inputs, it takes paths with terminal blank, paths with terminal symbol, and the output probability matrix at that particular time instant. So the column of probability values over all symbols in the vocabulary at time step t. And as its output, you get new paths which terminate with a blank and their corresponding blank path score. So now let's look at the code for this function. First, this diagram illustrates the different transitions that this function models. So basically this function extends all paths with a blank. So paths which either end with symbols or with blanks themselves are extended using these arrows to paths which end with a blank. So the transitions are from all kinds of lines to blank lines, and that is what is highlighted in this figure. This is the pseudocode for the function extend with blank. This function maintains two variables, which is the updated paths with terminal blank, a set of all the updated paths with a blank at the end, and the dictionary updated blank path score, whose keys are the updated paths with terminal blank and whose values are the forward probabilities of those particular paths. And that is what is returned by the function. So for the first step of the function, we loop through all the paths in which end with a blank, And now, since adding a blank does not change a symbol sequence, the path remains the same, and we simply add the path to our updated paths with terminal blank set, and correspondingly we initialize their forward probability scores accordingly. Whenever you calculate the forward probability of a particular path, you first retrieve its existing forward probability score of the path up till the t minus 1th step, basically, and then multiply it with the probability of the particular symbol with which you are extending it at the current time step, and that gives you the forward probability of your particular path. And if your particular path under consideration is already existing in your set of updated paths that you are adding to, then you simply add this forward probability score to the existing value. Otherwise, you need to make a new entry in your dictionary. This is just an implementation detail that you will come across when implementing this for homework 3. Moving on, this figure illustrates the step that we just saw. Here we basically try to transition from paths which end with a blank, and we try to transition to again adding a blank, so to the same blank lines. That is why we see that the horizontal edges are highlighted here, because we try to transition from blank lines to blank lines. We now move to the second part of this function, which is for all the paths which end with the terminal symbol. Now, again, even when a path ends with a terminal symbol, adding a blank will not change the path. So you simply directly check if that particular path, as obtained from the set of paths with terminal symbol, exists in your updated path set. And if it already exists, like I mentioned before, you simply add to its forward probability score by computing the current path's probability score accordingly. However, if it doesn't, then you first need to add this new path to your set of updated paths, and then initialize the dictionary of forward probability scores with the probability score of the current path, which you obtain by considering the probability score of the path up till the t minus 1th instant, which is what path score of path gives you, and then you multiply it with the probability of a blank occurring at the current time instant. Also note that the variables path score and blank path score are global variables for this very reason, because they are accessed by multiple functions to directly obtain the forward probability of certain paths and update their forward probability on being extended with different symbols in the function. Finally, this function will return the updated paths and their forward probability scores. This figure illustrates the what we just saw in this function. So the transition was made from the paths which ended with symbols so that they could be extended by blanks. So the arrows point from symbol lines to blank lines, and thus they are these arrows which have been highlighted in the figure. Now we move on to the next function in the beam search algorithm, which is called the extend with symbol. Its functionality is very similar to the extend with blank function, only that it aims to extend the existing paths with a symbol instead of a blank. So for its inputs, again, it will also require paths with the terminal blank and paths with the terminal symbol, along with the symbol set and the probabilities across all the symbols in the vocabulary at the current time step. And for its output, you get new paths with terminal symbols and also their corresponding forward probability scores. So this is what the function aims to do. For all the paths ending either with symbols or blanks, it aims to extend them by adding a symbol at its end, and that is what these lines represent, which are highlighted in the figure. This is the pseudocode for the function extending with symbols in beam search. Again, notice the variables updated paths with terminal symbol and updated path score. Updated paths with terminal symbol is a set of all the new updated paths obtained from this particular function by adding a symbol to the end of the path, and the corresponding forward probability scores is maintained in this dictionary of updated path score. So we start by looking at the first part of this function, where you loop through all the paths which end with a blank and then try to add a symbol to them. So for that you need to loop through all the symbols in the symbol set, and since adding a symbol to a path which ends with a blank always creates a new path, you can directly create a new path by adding these two strings, path and the new symbol, and after that you make a new entry in your set by adding the new path to it, and you also update the corresponding value in the dictionary by computing the forward probability of the new path and making a new entry in the dictionary. So this diagram illustrates the step that we just saw. Basically, you considered only those paths which terminated with a blank, and then you try to extend them using different symbols from your symbol set. So these represent all the arrows from blank lines to symbol lines, which have been highlighted here. For the next part of the code, you consider all the paths which terminate with a symbol, and now you try to extend them from using symbols from the symbol set. If C represents the particular symbol, you need to make sure that the last symbol in the path is not the same symbol with which you're trying to extend the path, because if it were, then the path would remain exactly the same. For example, S2 S1 extended with another S1 is the same as S2 S1, so there's no need to append to the path. However, if S2 S1 was extended with the symbol S2, then this is different from simply S2 S1. And so the symbol needs to be added at the end of the path. So that is what this particular condition checks, whether the two symbols are the same and whether or not you need to add that symbol at the end of the path. So now if this new path that you have obtained already exists in your updated path set, then you simply need to update its forward probability using the forward probability of the path you have just calculated. Otherwise, you need to make a new entry in the set and initialize the forward probability in the updated path score dictionary using the forward probability you just calculated for the current path, which is basically the forward probability of the current path's first t minus 1 characters obtained by path score of path multiplied with the output probability of the current symbol occurring at the current time step. Finally, you of course return the updated paths which now terminate with a symbol and their corresponding path scores. So this figure represents the step that we just performed. We only considered the paths which terminate with a symbol, and we aim to extend them with another symbol, and that is why you see these particular arrows which are both diagonal as well as horizontal highlighted in this figure. Now we return to the routine that we skipped initially, which is prune. So what pruning does is it deletes unpromising paths from contention, and thus this is the essence of the beam search algorithm. This is how we try to be computationally efficient, by sort of discarding the paths which show less promise in the beginning itself. So in pruning, you need to take as input the new paths which terminate with a blank, new paths which terminate with a symbol, the new blank path score, the new path score, along with the beam width with which you want to perform pruning. So notice that in these T iterations, you first get the new paths which terminate with a blank or with a symbol by extending the paths with a blank or a symbol, and of course you obtain their corresponding forward probability scores as well. However, all of these are fed into the next iterations prune step, so that those paths and those paths which terminate with a blank or a symbol are pruned accordingly based on their scores. And the output of the prune step it would be paths with terminal blank and paths with terminal symbol along with their corresponding path scores, and these become the inputs to your functions extend with blank and extend with symbol in the same time step. So now let's look at how the prune function works. We will be considering pruning at this particular time instant, so that you can see an effective example of how pruning is useful. In the prune function, the variables that you need to keep in mind are the pruned blank path score, prune path scores, which these two are the dictionaries of the forward probability scores of paths which either end with a blank or end with a symbol. And of course, you also need to maintain the set of such paths which are called the prune paths with terminal blank and the prune paths with terminal symbol. Now we can look at the code step by step. The first part of the code is to gather all the relevant scores. This basically means that you try to create a list of all the scores of all the paths which either end with a blank or a symbol. So you simply keep appending to a scored list by iterating through all the paths which end with a blank or a symbol. This diagram illustrates the step that we just performed. The red circles represent the paths which terminate with a symbol, and the blue circles represent the paths which terminate with a blank. And we basically try to aggregate the scores from all these symbols. Now, once we have this score list, we can sort it in the descending order and decide a cutoff for this score list. So basically, if the length of your entire score list is less than your beam width, that means that you do not have to prune at all. You have very few paths and your beam width is sufficiently large and pruning is not necessary. However, if the length is greater, then since you are allowed to have only a subset of the entire paths set that you have, you choose to take the paths with the k highest scores. So the cutoff would be the kth largest score, so that all the paths with scores greater than that particular cutoff, which would be exactly k in number, can be retained, and the rest of the paths can be discarded. So based on the value of beam width and the length of the score list that you have obtained, you decide what the cutoff should be. If the beam width is lesser, then the cutoff is the kth largest value of your score list, and otherwise it's simply the last value of your score list, which would mean that all the values in your score list are greater than or equal to that value, and thus all the scores and all the paths are retained and nothing is pruned. Now we move to the next part, which is basically to loop through all the paths which end with a blank, check if their scores are greater than the cutoff determined in the previous step, and if they are added to the final prune paths with terminal blank, and their dictionary of the blank path score is updated accordingly with the forward probability score. Otherwise, the path is not added to this final set and thus automatically discarded. So this diagram represents the step that we just saw. You can see that two of the previously blue circles have now been blackened out, which means that they have been pruned, and now these circles or their children will be discarded and will not contribute to further computation, and you only retain the blank rows whose scores are above the cutoff, for example this blue circle. Now we move to the next part of the uh, pruning function, which is to do exactly what you did for the pruned paths, to obtain the pruned paths with terminal blank. You now, to obtain the pruned paths with terminal symbol, you now loop through all the paths which end with a symbol and check if their scores are greater than the cutoff, and only then you add them to the final set of pruned paths with terminal symbol and update their pruned path score in the dictionary with the forward probability score. And of course, those which do not pass this if condition are automatically discarded. This figure illustrates the step we just saw. You can see that some of the circles which were previously red are now blackened out because their forward probability values were lesser than the cutoff, and so they were pruned. And the red circles are those whose values were greater than the cutoff, and so those paths and their corresponding probability scores were automatically added to your final updated paths with terminal symbol. So as a result of the last two steps we just saw, we see that the following circles have been blackened out and pruned, and only those values whose only those paths whose scores are greater than the cutoff are retained. And in this case, since 4 values are retained, we can assume that the beam width used here was 4. One important note is that pruning should be done at the beginning of your loop and not at the end. There are two reasons for this. Firstly, your symbol set might be quite large or your beam width might be small, and that means that right after the initialize paths function is called, you may require pruning because the number of symbols being considered after all the paths are initialized might already be too large. And a more important reason is that we do not want to prune after the very last time step. After we've calculated all the extended paths, after extending them with blanks and with symbols, we do not want to lose information by pruning out these paths. Instead, we can just collapse these paths so that in case they represent the same final path, so we could merge their forward probabilities and thus use more information to finally obtain the best path by taking the argmax over all the final path scores. So pruning after the final time step would only lead to a suboptimal solution. So we do not want to prune after the final step and retain as much information as possible. Now we move to the last function in the beam search algorithm, which is to merge identical paths. This function takes as its input all the outputs that we have obtained from the extend with blank and extend with symbol functions, namely the new paths with terminal blank, new paths with terminal symbol, and their corresponding forward probability scores. The merge identical paths function will return the final set of merged paths along with their final probability scores, the forward probabilities of those paths which have been merged basically. Let's now look at the function in detail. So basically what we are trying to do is to merge paths so that you end up adding the forward probability distribution of identical paths and not count them as two separate paths. For example, here the paths S2 and S2 blank basically represent the same path, but since we have been maintaining two separate sets after extending paths with a blank and extending them with symbols, these paths will be counted as two separate paths until and unless you call this special merge identical paths function and merge them together and add their forward probability scores. So basically you're trying to consolidate the forward probability scores before you take an argmax over all of them to get your best possible path. Similarly, you would do this for S1 and S1 blank as well. So now let's look at the code for this function. It's pretty straightforward. You know that all the paths with terminal symbols are definitely unique and will remain in your final list. So you could just initialize your merged paths with the set paths with terminal symbol and initialize your dictionary final path score with the dictionary path score. Now for paths with terminal blanks, they will either contribute to existing identical paths from the paths with terminal symbol set, or they will be included in the final set. So check for each of these paths with a terminal blank if they already exist in merged paths, and if they do, then you consolidate these forward probability scores by adding to the dictionary of final path score. Otherwise, you create a new addition in the set merged paths and initialize the dictionary final path score with the forward probability of this particular path. Finally, you return the set of merged paths and the dictionary of its final forward probability scores. And now the very last step of the algorithm would be to pick the best path, and that would be a simple argmax operation over all the final path scores. So basically the best path would be the one with the highest forward probability score, and since we aggregate it over all our all possible occurrences of our order synchronous sequence, we get the best possible order synchronous symbol sequence given the particular beam width. While this function may not exactly be may not always exactly be accurate. It might be possible that one of the paths that you discarded earlier on later goes on to have a very high final forward probability. It is a trade-off basically between computational complexity and accuracy. If your beam width was 1, then you are basically performing the greedy decode algorithm. However, if your beam width was infinity, you are performing the algorithm where you explicitly decode all possible symbol sequences. And while that algorithm will definitely give you the correct answer, it is computationally very inefficient. And while greedy decode is computationally very efficient, it gives you a very bad solution. The solution is definitely suboptimal. So you sort of try to balance both these attributes and strike a balance by tuning the hyperparameter beam width accordingly. So this brings us to the end of the first part of this recitation, and Amla will now run through the code that you require for homework 3. Thank you and all the best.
In the first part of today's recitation, Soumya walked us through the beam search algorithm for CTC decoding. We will now look at some PyTorch functionalities and external libraries that are very useful for Homework 3 Part 2. You must have realized by now that calculating the CTC loss for training sequence-to-sequence models is no easy task, especially when you're batching your training instances. In the past, people have used third-party libraries like Warp CTC for calculating the loss, but starting version 1.1, PyTorch started providing built-in support for the CTC loss. And for homework 3, we strongly recommend using nn.ctc loss while training your model. To demonstrate how to use this function, let's look at a toy task where the goal is to predict the pronunciation of an English word given its spelling. Here we define a pronunciation as the sequence of phonemes associated with a word. CTC is probably not the best framework for this task because some letters actually map to a sequence of more than one phoneme. For example, the letter X maps to two phonemes K and S. But we don't encounter such examples in our simplified data, so the CTC framework works pretty well with it. Now let's look at the code for our toy task. In snippet 1, we've initialized our training data. It has 12 words containing only the letters E, I, N, S, and T, and we have 7 phonemes in total. So as you can see here, the word C maps to the phonemes S and E. The word set maps to the phonemes S, E, and T. Note that if there are P phonemes for the output, they should be indexed as 1 to P, not 0 to P minus 1. This is because we have an additional blank symbol while doing CTC decoding, and index 0 is reserved for the blank symbol by default. Because of this, the output will have P plus 1 classes instead of just P, since blank is also an output class. In snippets 2 and 3, we do some data pre-processing and we define our model. The model that we're using for this toy task is pretty simple. It just uses a bidirectional LSTM and computes the probabilities over all the classes for each letter in the word. The important part is the pre-processing code in snippet 2. Here, X is a list of source sequences, each of which is a word, and Y is a list of the corresponding target sequences consisting of phonemes. Since X and Y have variable length sequences, we pad them using the pad_sequence function. As you can see in the output of the code snippet, X and Y have different shapes. This is because we're setting the batch first argument to true while padding Y, but not while padding X. We have to do this because the nn.ctc loss function requires inputs in a very specific shape and format. And the PyTorch documentation for the nn.ctc loss function is very comprehensive, and you should read it carefully while writing and debugging your code for homework 3 part 2 because of the same reason. All these requirements are specified in detail in the documentation, but let's take a quick look at them anyway. So the forward function of nn.ctc loss takes 4 arguments to compute the loss. The first is log probs, which stands for log probabilities. The function expects this to be a tensor of size t cross n cross c, where t is the length of the largest input sequence in the batch, n is the batch size, and c is the number of classes, which is equal to the number of phonemes plus 1. Note that this is different from most loss functions in torch.nn in the sense that they take logits or probabilities as inputs, whereas nn.ctc loss takes log probabilities instead. We handle this in our model by calculating the log softmax over the logits in the forward function before returning the output, as seen in the highlighted part of snippet 3. Over here, the input to the log softmax function is the dimension across which we're performing the softmax operation. The second argument is targets, which contains the target sequence for each word in the input. It expects a tensor of size n cross s, where n is the batch size and s is the length of the longest output sequence. This argument expects batch first inputs while log probs does not, and this is why we had to pad y over here with batch first equals true in the first place. The third argument is input lengths, which is the length of the sequences in log probs. Note that this is not necessarily the same as the length of the input sequences to the model. In this example and in homework 3, they are the same, but if your model used CNNs or pyramidal RNNs instead, then the length of the sequences would have changed, and you would have to compute the length of the output sequences of the models carefully. In code snippet 3, you can see that the length does not change, but we return the output lengths along with the log probabilities anyway. I strongly recommend doing this whether your network changes the length of the sequences or not, because it makes life much easier while debugging your code. So now that we understand the arguments to the forward function of nn.ctc loss, let's take a look at how we can use this function to train the model. Snippet 4 contains the training loop. So over here, we're batching all the training instances together, and because there are only a few of them, so this gives us one training batch. And in each epoch, we pass the batch through the model, we obtain the log probabilities and output lengths, we calculate the loss, and we update the model parameters after performing the backward propagation and after invoking the optimizer step. Now, if you run this snippet in your local machine on a Jupyter notebook, it'll probably just take less than a second to run, because the model is very simple and because the training data set is also pretty small. So that was it for the training part of our toy task. Now that we've trained our network, let's look at how to perform inference. At inference time, we need to go a step further and generate the most probable phoneme sequence for a word given the log probabilities over all the symbols. Currently, PyTorch does not have inbuilt support for CTC decoding, so we recommend using the CTC decode library for inference. We've included instructions for installing CTC decode in this notebook, and it will be uploaded on the website soon if it's not there already. You can follow these instructions while installing the library on your computer or on your AWS machine. And if you run into any trouble, you feel free to make a post on Piazza about the same. To test your installation, you can run the code snippet in 6. We've also included some of the common errors that you might encounter and how to handle them. And if everything is in place, you should see an output like this after running the code. Unfortunately, CTC decode doesn't have any documentation, and the only way to understand it is to read the code. So we've also included some documentation in this notebook for your reference. The CTC beam decoder, which is the main class from the library under consideration, is the constructor for this class takes 4 parameters. The first is phonemes, which is just a list of characters whose length is equal to p+1, where p is the number of phonemes. Note that the contents of this list are not actually used in the code, so the list doesn't need to contain the actual phonemes. And as long as the length of the list is equal to p+1, you'll be good to go. This is pretty strange behavior, but it's just how the code is structured, and the rest of and that's why we follow it. The rest of the parameters to the constructor are self-explanatory. So we have the BIM width here, which is a hyperparameter, and for our toy task, we've set that to 4, as you'll see in a few minutes. The number of processes can just be set to the number of CPU cores on your machine. And we have log probs input, which is a flag, which when set to true, the model expects log probabilities instead of plain probabilities. Now let's take a look at the decode function, which is the main function that we use to perform the CTC decode. The first argument to this function is probs, and this should be the log probabilities if the log probs input parameter of the constructor is set to true, which we recommend doing because you can pass the outputs of your model as they are without making many changes. Note that the expected shape of this tensor is n cross t cross c, not t cross n cross c as it was in nn.ctc loss. So you will have to transpose the output of your model accordingly, as shown in this highlighted part. The second argument is just the length of the sequences in probes, and the function returns 4 outputs in total, but we're only interested in the first one, which contains the top beam width number of decoded sequences. Now the shape of this first output is n cross b cross t, where b is the beam width. And since we're only interested in the best sequence, will just be looking at index 0 of the second dimension here. So let's try using the CTC decode library for our toy task. The 7th snippet just contains a helper function for visualizing the generated output. In snippet 8, we pre-process the test data, and we instantiate the decoder with a beam width of 4, and we pass the input sequences through the model and obtain the log probabilities over the phonemes and the length of the sequences. And finally, we pass these outputs through the decode function and obtain test underscore y, which is just which just contains the top 4 decoded sequences for each test instance. Now let's visualize the alignment of the top pronunciations that we obtained with the words in the test set. So in these visualizations, the x-axis contains phonemes from the phoneme list, and the y-axis just contains letters in the word. So in the first example, we obtain a mapping from the word T to its corresponding phonemes T and E. So over here, T is correctly aligned with the phoneme T, and the next two letters are correctly aligned with the phoneme E. Similarly, for tint, we can see that T has equal probabilities for phonemes S and T. I just mainly aligns to the phoneme E, and N aligns to the phoneme N, and T aligns to the phoneme T. And you can also see the alignments for the other two examples for sign and scent over here. As we just saw, it's pretty easy to use CTC decoder over a batch of inputs. There is a caveat though. If you provide invalid arguments to the decode function, for example, if your inputs have the wrong shape or they're in the wrong range of values, then your program will crash silently without providing any meaningful error message. It is very difficult to debug such errors, so I would recommend printing out the inputs to the function and their shapes while debugging the code to figure out what is causing the program to crash. So this is an example of a faulty code. So if you run the snippet in your Jupyter notebook, it will cause your Jupyter notebook to crash. And while it's okay to make that error in this toy example, you probably wouldn't want to do it in your main code. So it's very important to be careful while using the decode function. So that's it for recitation 8. As always, if you have any questions about the content that was covered in this recitation, feel free to post a question on Piazza. And good luck for homework 3.